and welcome to session 4 of Unit 5. This session will introduce you to track measurements of radioactivity. By the end of this session, you should be able to explain track measurements, solid-state nuclear track detectors, and cloud and bubble chambers. The tracks are subatomic particles such as protons, electrons, and mesons produced by nuclear reactions and can be recorded by photographic means. The tracks are formed by these nuclear particles in cloud chambers, in solid and in photographic emulsions. The tracks, they basically reveal the individual nuclear reactions and radioactive decay processes. These tracks that are formed can be directly observed by the naked eye in clouds and in bubble chambers. The tracks have short lifespan, and so in order to keep them, we need to have a photographic record of them. So mostly there is permanent record through photography, and that's how we are able to at least have a record of these tracks. Let us look at cloud chambers, how they come into existence. So in 1994, there was this Scottish physicist called Charles Wilson who was interested in knowing more about the odd shadows that can sometimes be formed on cloud tops by mountain climbers. Mostly these are called the broken spectra. So he has come up with a way to build his own device that will allow him to form his own mini clouds inside that device, and he named that device the cloud chamber. So the device was designed that he could keep the air inside supersaturated with water. Supersaturated means that the air will be holding more vapor than it would normally hold at that particular pressure and temperature. So he quickly realized that as charged particles pass through his cloud chamber, they were able to ionize some other molecules, and this resulted in ions that caused water vapor to condense. Over the next few years, Wilson was able to see the path through which the charged particles had passed just by looking for the little vapor trails forming in the chamber. Let us look at bubble chambers. So the bubble chambers are exact opposite of the cloud chambers, in that instead of the supersaturated vapor that can condense into a liquid when it comes to the cloud chambers, with bubble chambers there is a use of liquefied gas that is at a very low pressure, that it is on the edge of boiling back into gas. So as the particles pass through this liquid, they cause it to boil into gas, leaving trails of bubbles along its path. The cloud chambers and then the bubble chambers are usually operated with a constant magnetic field perpendicular to the path of the particles. So when they are operated this way, then we are able to observe the particles as they spin through a spiral pattern. Let us look at solid-state nuclear track detectors, or SSNTDs. They are basically a sample of solid material. It could be photographic emulsion or crystal or glass or plastic that has been exposed to nuclear radiation, etched and examined by microscope or examined microscopically. The tracks of nuclear particles are etched faster than the bulk material, and the size and shape of these tracks yield information about the mass, charge, energy, and detection of motion of the particles. Let us consider some few advantages of the SSNTD. It gives this detailed information of individual particles. So the SSNTD is able to give enough and adequate information about each of the radiations or the particles. Then it is persistent, and so it allows for measurement to be made over a long period of time. Also, it is simple, cheap, and robust in construction than other detectors. So the SSNTDs are commonly used to study cosmic rays, long-lived radioactive elements, reading concentration in houses, and the age of geological samples. A material that is commonly used in SSNTDs is the polyallyl diglycol carbonate, abbreviated as PADC, and is also known as the TASTRAC or the CR39. This is a clear, colorless, and a rigid plastic which has a chemical formula of C12H18O7. Radiation damages are usually exposed by etching, and this is usually performed by the use of caustic alkalis such as the sodium hydroxide, mostly at elevated temperature for several hours. The main types of SSNTDs are the photographic emulsions, the crystals, and the glasses and plastics. This is a trial question that I want you to have a look at.